Welcome back to part 2 of Wednesday, November the 4th. We still don't have an outcome to the election. At least I haven't checked. And so,
You don't. I think it has changed.
yeah, don't ask questions you don't want the answer to. So, when we're doing all of this, the shapes, the reason why the shapes are important again is because it determines the properties. And so what I want to talk about now is the difference between polar and nonpolar. How do you tell if a molecule is polar or not? Because we've just I've up to this point just been telling you this is polar. We look for fluorine, oxygen, nitrogen, or chlorine, meaning we're going to have a polar bond. But what really, how can we have some kind of system to be able to determine whether the molecule is polar? Because that determines what type of IMS it's going to have, and really ultimately whether it's a solid, liquid, or a gas at room temperature. So let's just talk about polar molecules, and then we'll get into properties of covalent substances. So, polar molecules must, number one, contain at least one polar covalent bond. Okay, so how do we tell if it's a polar covalent bond? What do we look for to determine whether it's a polar bond or not? The differences in electronegativity, right? Okay, and which four are a big four most electronegative elements? Most electronegative elements most electronegative elements contain either fluorine, oxygen, nitrogen, or chlorine. Now that doesn't mean that they're the only ones that form polar bonds, but if they're present, more than likely the bond is polar. So put your phone away, please, and let's go ahead and sit up. You're wide awake while you're playing with Tinker Toys. Okay. Fluorine, oxygen, nitrogen, and chlorine. So, if we have one of these, we're going to have a polar bond. It's an uneven sharing of electrons. Okay? Which causes an uneven distribution. The electrons are more towards one than they are towards the other. Okay? So you got to have at least a polar bond. Now there is a scale that we use. We can let X, and I don't really follow this because you're not going to really know the exact electronegativities because the generic periodic table you have doesn't have it, so we only know trends. But generally speaking, let X equal the difference in electronegativity, En. Okay? This is En. The difference in electronegativity. If X is less than or equal to 0.3, we call it a nonpolar bond. What does nonpolar mean? It's not a rhetorical question. I'm expecting an answer. It's not polar, meaning what about the electrons? They're evenly shared symmetrically, even distribution of electrons. Okay? Because there's very little difference in electronegativities, and so neither one can pull the electron very far from the other one. They're pretty close. That's why most nonmetals with nonmetals, other than phone call, most nonmetal with nonmetal are going to be relatively close to one another. And so they're fairly nonpolar. They might rarely get out of this. If X is greater, whoops, the other way. X is greater than 0.3, but less than or equal to 1.7, we call it a polar bond. And if X is greater than 1.7, we call it a ionic bond. This is the periodic table that you guys have, okay? If we look at the back side of that periodic table, so everybody, you guys go copy and come in and pull the screen down once the light comes on. And then y'all finish copying and then I'm gonna pull the screen down. Still pretty small, but if we look up here, the top in the black is the difference in electronegativities between any two atoms. Notice that at 0.3, we're like at 2% ionic, the percent ionic character here. Sure looks blurry. Still blurry. Okay, it's a very low percent ionic character, which means we don't have very much uneven sharing and not much distribution. Between 0.3 and 1.7, what happens at 1.7?
Goes over 50.
It's 51% ionic. So we're going to just say it's an ionic bond versus, because it's more ionic than it is covalent, when the difference in electronegativity is greater than 1.7. Okay? Now, is it fully transferred? No. That generally doesn't happen until you put it into water. The water ionizes, it really causes the complete separation of the electrons once you put it into water. Okay? So, we just look here. So we have this scale. But generally speaking, again, you don't have the exact electronegativities to be able to subtract. So we just go by trends. Which is why, again, we look at phone call. But the reality is that any two atoms that have differing electronegativities could have some slight polarity to it if they're not the exact atom. Because there'll be a little bit of a difference in electronegativity. Fancy term, a thing called dipole moment. Moments of physics terms. The dipole moment is a measure of a molecule's polarity. The bigger the dipole moment, the more polar it is. And so if you ever see the term dipole moment, that simply means the molecule's polar. Something has a dipole moment, it's polar. If it doesn't, it's nonpolar. So that's just a way of measuring that. Okay. So the first criteria is that you got to have a polar bond. For us, the practicality of that is we're going to look for phone call. But just because that's present doesn't mean that it's necessarily going to be polar, because we have to have the second. This is not a or, this is a must, this is an and. And number two, okay, the polar molecules must be asymmetrical. And I always tell people, when you write the word asymmetrical, there's only one S. You don't want to be an S when you write asymmetrical. Okay? Only one S, two M's. What does the word asymmetrical mean?
Not symmetrical.
Not symmetrical. Okay? Now, I want to try and say this differently than I've said it in years past, because the wording is real important on this. Okay? Asymmetrical molecules, I'm going to say it anyway, generally, and this is the key here, generally contain a lone pair on the central atom, at least one, or all the bonding atoms are not the same. Okay? That's your X's, and AX4, if your X's aren't all the same. For example, CCl4, carbon tetrachloride. Okay? Do we have a polar bond? Yes, we have 4 polar bonds. But because they're evenly distributed, because they're at the corners of a tetrahedron, this fluorine, chlorine is pulling this way, this chlorine is pulling this way, that way, and this way. Because it's symmetrical, all those pulls cancel out. Those of you that have physics or engineering, we talk about vectors, okay? When you have opposing forces, when your equilibrant is equal to 0, there's no net force, there's no net motion. That's what you want to try to do when you balance something. You try and make all the forces counteract one another so it doesn't move. Okay? So if it's symmetrical, all of the uneven poles cancel each other out and the molecule ends up being nonpolar. This is symmetrical and nonpolar. Now here's the deal. If it's symmetrical, it doesn't matter what type of bond you have. Polar molecules have to be asymmetrical. So as soon as you see a molecule symmetrical, then you know it's a nonpolar molecule, no matter what type of bonds there are. Okay? Symmetrical molecules are always nonpolar. So, if I just change this to this, now are all my bonding atoms the same? No. So now I have 3 of them that are pulling 1, 2, 3, but there's nothing on this other side pulling to balance these out, so we end up having a net pull of electrons towards this side of the molecule and electron deficient over here on this side of the molecule. We end up getting a polar molecule. So this one's asymmetrical polar, because I have polar bonds and it's asymmetrical. Move it over here to this side. Thank you. I'm trying to be bossy. If I look at NH3, what's the shape of this molecule? Trigonal pyramidal, right? So that means, again, when I build this, okay, and I don't have one, this is my lone pair, is the stick, okay? Now notice, the nitrogen is the more electronegative element, so the electrons are being pulled here, and being pulled there, up. Are they going to cancel each other out? No, this is an asymmetrical molecule. Okay? Now, just about every molecule that has lone pair on the central atom is going to be asymmetrical, but you're not allowed to say it's asymmetrical because it has lone pair electrons. It's asymmetrical because of its pyramidal shape. Okay? It's not the lone pair that make it asymmetrical. It's the shape that makes it asymmetrical. It's just all of the ones that have lone pair are asymmetrical. Okay? But you say it's asymmetrical due to the shape. Due to the asymmetrical pyramidal shape of NH3, there's an uneven distribution of electrons causing the molecule to be polar. You don't say it has lone pair on it and so it's polar. Okay? It's very, 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 very important. Okay? The asymmetrical shape, the pyramidal shape, causes an uneven distribution of electrons, making the molecule polar. Even water. When we talk about water, sometimes we do this, because what's the shape of water going to be? AX2E2 has always been, right? But you can still draw the Lewis dot structure to look like that. That's 100% fine Lewis dot structure. But we know AX2E2, it's bent. So the reality is when you're looking at water, okay, you can be looking at it bent, Or you can be looking at it with no depth perception as linear. Okay? You're drawing something in 2 dimensions that actually exists in 3. So as a result, we have to just always trust our AX formula, not what the Lewis dot structure looks like for the shape. Okay? Now, so this is asymmetrical, polar. This is asymmetrical and polar. Okay? Now, I'm going to just continue under asymmetrical here. There are 2 exceptions that you have to know. And this is why we can't say it's asymmetrical because it has lone pair, because not all molecules that have lone pair on the central atom are asymmetrical, because there's these 2 exceptions. Two exceptions to molecules with lone pair electrons on the central atom. Number 1 is AX4E2, square planar. Oh, I don't have this built anymore, but if you remember the square planar, you had the 1 in the center, and then you had the 4 that around it, then a lone pair on top, a lone pair on the bottom. So it's got lone pair, but it's still a very symmetrical molecule. And the other one is AX2E3. What shape was that one? Linear, good. Even though nobody said it. Okay? Linear is going to be, as long as the same thing on both sides, then it's going to be, these both are symmetrical. Any other compound, any other AX formula with an E in it is going to be asymmetrical. Even if there are no lone pair, if all the bonding atoms aren't the same, it's asymmetrical. So even if I go carbon, chlorine, chlorine, hydrogen, hydrogen, that looks symmetrical because we're drawing it in 2 dimensions. But if I again look at this, and I have chlorine pulling this way, it doesn't matter where. If I have a chlorine pulling this way, and another one pulling either this way or this way, it doesn't matter which one you put it on, there's not going to be a balance on the other side. They're not really opposite of one another, even though the Lewis dot structure says they're opposite. Because 2 dimensions, 3 dimensions. So you can't trust your Lewis dot structure for symmetry. You have to trust the 2 rules. And always, it's the shape of the molecule that determines the symmetry, not the number of lone pair. Okay? So, when we look at our molecules then, oh, I wish I had just a blank sheet. When we look at this Lewis dot structure, how many times can we use this same worksheet? Okay? When you look at your structure here, SiO2, what's the shape of SiO2?
Linear.
Linear. What's the AX formula for it?
AX2.
AX2. So are there any lone pair on the central atom?
No.
Are the bonding atoms the same? What does that mean about the symmetry then? Symmetrical. Do you have polar bonds?
No.
Do you have polar bonds? Since phone calls, fluorine, oxygen, nitrogen, and chlorine is present, yes, I have 2 polar bonds, but they're pulling exactly opposite directions, therefore they cancel each other out, and the molecule is nonpolar. Okay? When you look at CCl2F2, are there any lone pair on the central atom?
No.
But are the bonding atoms the same? No. So what do we know about the symmetry?
It's asymmetrical.
Asymmetrical. And so it's going to be polar. Now this one's not gonna be super polar because chlorine and fluorine are both big daddies, okay? But fluorine is significantly stronger. This is a 4, this is a 3. So it's gonna be an uneven pull, and so it's gonna be polar. But we would measure the dipole moment. Now NF3 is just gonna be like NH3, but again, we're gonna have a lone pair on the nitrogen. So is it symmetrical or is it asymmetrical? Due to its pyramidal shape, okay? And again, fluorine is, again, these are two big electronegative elements, but there's still gonna be a significant difference, and it's gonna be polar. So we should be able to tell now, just looking at the shape of the molecule, whether it's symmetrical or asymmetrical, whether the molecule is polar or not. Because that's going to determine, again, if non-polar, it's only got London dispersion forces, but if it's polar, it has dipole, and hydrogen, or possibly hydrogen bonds. Okay? Greatly changes. So we got one last thing to talk about, is the properties, going through the properties of covalent. We have actually two types of covalent substances, covalent molecular, which has the IMFs, and then covalent network, which we already kind of talked about briefly, as far as what are the properties of those and what are those things, and review that, okay? And then we're going to be close to being done, but then we got a bunch of AP practice problems to work through. Did you say the shape around each one?
Yeah.
Okay?
Would you just do it as the entire molecule or like?
No, you don't do, well, if any part of the molecule is polar, the molecule is polar. I think that's the question you're asking. Because the OH part's polar, okay? But the N and the O are pretty close, but you're still, whenever you have an OH, it's polar.